All right, so today we're going to be looking at work in physics. And so let's going to start with when a person lifts a weight or shovels snow, or let's say that they push on a vehicle or on a car that is stuck in some mud, then we say that that person is doing work. Or that work is being done. Well, we need to be careful with that because in physics, this is much different. In the sense that all of these examples have one thing in common. And that is, there is a force that is being applied over a distance. But that's not enough. So let's have a look at what in physics there are 3 conditions that need to be met for work to be done. So the first condition is going to be there has to be movement. So it doesn't matter how heavy of an object you're lifting, 100-pound weight, it doesn't matter. When you're holding an object in place, that is not work. The second condition is going to be there has to be a force applied. So again here, let's say that you are gliding on your bike down a hill, or let's say that you are skateboarding on, at your skateboard park without pedaling or without pushing. You are not doing work. Even though you are moving. And then the third condition that has to be met is the force and the distance or the movement in which the object is going must be applied in the same direction. So for example, I'll give you an example here. If I was lifting a backpack on my back, then that would be work because the direction of the force being applied is up and the backpack is also moving up onto my back. But then once the backpack is on and I start going to class, I'm not doing work anymore because I lifted the backpack onto my back, and so that's the force was done. But now the movement is no longer in that direction. Okay, I'll give you some examples of what work is and isn't. So here's this one. So as you can see here, we have somebody pushing on a crate, And so the force is being applied in one direction, but the box is not moving. And therefore, because it's not moving, there is no distance, and so no work is being done. In the next one, what we have is a person lifting a box, and a force is going in one direction. The direction is on the other. So if I was wearing a backpack, that would be the same thing. Okay. And again, this is an example of no work being done. Okay. So here is an example then of how, okay, hold on. This is an example of work. Let me get a picture here. This one. Okay. And so in this case, what we can see is we have somebody who is pushing a crate up a hill. And so we have a force going in that direction. And the direction of the movement of the box is also in the same direction. Okay, so I'm going to write the direction that way. Okay, so you can see here work, an example of work being done. All right, now the formula, let's go back to that. Here we go. So the formula for work, I think I'm going to change colors here. Work is equal to a force times a distance, okay? Where work is going to be measured in joules, but we'll come back to that. And then I have a force, which we learned last time. It is in newtons. And a distance, which is measured in meters. And then work is newtons times meter. And a newton times meter is actually known as a joule. Oh, this is not cooperating. Let me see if I can blow this up. J. There we go. So joules. Now, one thing to keep in mind again from last week is a force. We learned about force last week, and we learned that the formula for force is mass times acceleration. And so we can apply that to our work formula by saying that work is equal to mass times acceleration, force, times a distance. So it's kind of easy to remember with MAD, M-A, and then D. Let's try an example together. We'll do an easy one first, sort of a plug and play, easy example. So let's start with example 1. And we have a force of 800 newtons is needed to push a car across a parking lot. And remember that if the car wasn't moving, we would not have any work, right? We're applying a force, but we have to have a distance. So if the car moves 20 meters, how much work is being done? A good point to start is to write down our variables. So force, and I have my distance, and then I'm looking for work. Now this is not particularly useful now, but later we can see that we have a force times a distance. Plug that in, and I get 16,000 joules. Now I need my answer to be in 2 significant digits because I can see there 2 significant digits for my distance. So I can divide by 1,000. And so if I divide by 1,000, I get 16 kilojoules, the same way that we had kilonewtons. Or scientific notation, 1.6 times 10 to the 4 joules. So those two are the acceptable answers for that question. Let's try one more. And again, let me remind you to pause the video and try these on your own. How much work is being done by a forklift that raises a 60 kilogram crate a distance of 10 meters. Okay, so again, the forklift is applying a force up and the crate is moving up. Let's put on some variables or write down what we know. Work is what we're looking for. Mass, we have at 60 kilograms. We have a distance. And we're gonna need our formula. Work force times the distance, and I know that force is mass times acceleration. Put that in brackets. Here we go. And so then I have my mass, I have my distance, but I don't have my acceleration, but I do have g. Remember g, the acceleration due to gravity, 9.81 meters per second square. We learned it last time. So then now I can put in my mass at 60 kilograms. I have my acceleration due to gravity because I'm lifting something straight up. And the distance is 10 meters. And when it all comes together, it is going to be 5,886 joules. And probably the two significant digits, the easiest way for me to do it is divide by 1,000. So 5.9 kilojoules, or you can have it in scientific notation, but 5.9 kilojoules works pretty easy that way. Okay. Now for example 3, what we're going to do is we're going to give you a question that has sort of everything but the kitchen sink. So everything we've learned so far for this particular question. And I'm going to remind you again, pause the video after the write down and try it. So example 3, we have 65 kilojoules of work is applied to push a box 10 meters. If the box moves from rest, 0, to 100 meters per second in 2 seconds, what is the mass of the box? And then we could take it even more one step and say, what if we wanted to calculate what is the weight of the box? Remembering that mass and weight are not the same thing. The mass is, remember, if I took all of your matter and squashed it all together into a ball, let's say, then that's what the amount of kilograms would be, whereas the weight has to do with the acceleration due to gravity, right? So the work is 65 kilojoules and the distance is 10 meters. Let me write down, I have an initial speed and I have a final speed. And I also have a change in time, 2.0 seconds. Let's look at some formulas. Oh, first of all, I'm looking for mass and then I'm going to be looking for weight. Okay, just so that we have those clear. All right. back to my pen. And work is mass, acceleration, and distance. So force times the distance. And so then I have, let's see, what do I have? Let's mark this down. So I have the work and the distance and mass is what I'm looking for. So I'm going to put a question mark. And can I figure out acceleration? Yes, I can. Let's see. Acceleration is final speed minus initial divided by our time. And easy peasy, we can figure that out. So we have our final was 100 meters per second and 0 meters per second. And my time was 2.0 seconds. And so this box is moving at 50 meters per second squared that's the acceleration. And so now we can plug these numbers in, but I'm looking for the mass. So the work divided by the acceleration and the distance. Let's see how I got that formula. I want to get mass by itself, so I got to divide by A, that cancels, divide by D, that cancels. Whatever I do to one side of the equal sign, I have to do to the other. So that's how I got that formula. That's algebra. And so let's plug that in. So 65 kilojoules, or also we could write down as 65,000 joules, because it's kilo, right? So times 1,000. And divided by my acceleration, 50 meters per second squared, and divided by my distance, which is 10 meters. And so 65,000 divided by 10 is 6,500, and then divided by 50 again, I'm looking at 130 kilograms. So that is the mass, but what about the weight? Okay, so first we can write it in scientific notation, but we could just leave it in our calculator for the time being. So we're using the 2 significant digits for the answer, but we can just leave it in the calculator. And let's figure out, not big W, little w, weight, mass times the acceleration due to gravity. So the 1.3 or 130 kilograms times 9.81 meters per second squared. Let's calculate that really quick. 30 times 9.81, and it's almost like times 10, right? And so I should end up with 1,275 kilograms, or again, in 2 significant digits. I could change that up to, again, because of that 2 significant digits there, just in case you didn't see it. So we get 1.3 times 10 to the 3 kilograms. Okay, so 1,300 kilograms really is what the weight of the crate was. So that's the mass, or as this one is the weight. All right. So that's that question. Let me remind you to make sure that you pause the videos and try these on your own. I'm going to be putting up a worksheet for you guys to try with all of these questions on work for you to do different practice. And then I'm going to be posting the key for that tomorrow, and I'm going to be posting the key from your previous worksheet in just a little bit. Okay? So again, try these on your own before you look at the key, and I will see you tomorrow at our Google Meet. Bye-bye.